Please open in your learning workbooks to page 179 as we solve some ALEKS problems involving the exponential function y equals e to the x, and specifically transformation of that function. Here's a problem. Below is the graph of y equals e to the x, shown here in green. Transform it to make the graph of y equals e to the negative x power plus 6. Give the domain and range of y equals e to the negative x power plus 6. All right, so this is the table of points that we saw in our previous example. And what I'd like to do here is take a moment to talk just a little bit about e to the x, and then we'll worry about transforming it. Okay, so same x values as in the previous video, same y values as in the previous video, although I have given you the exact y values here as well. For example, if you plug x equals 2 into here, you get y equals e squared, so the exact value is e squared. And that will be important because ALEKS does not just want decimal approximations. ALEKS is also interested in exact values. So I have supplemented the information presented in the previous video, showing that information here. All right, let's talk about the domain and the range of this particular graph. Identifying domain and range from a graph is something we did quite some time ago this semester, but hopefully it's a skill you still remember. Domain is a collection of all of the x's. That means it's a measure of how far your graph goes left or right. So let's see if we can look at this green graph and determine the domain. This is the part furthest to the left. That arrow is pointing left forever, therefore our domain begins at negative infinity. All right, this is the part of our graph that is the furthest to the right. This is an arrow that's actually pointing in two directions. It's mostly pointing up, but it is also pointing to the right. Now, when we measure domain, which one of those things do we care about? Up or right? The answer is right. Domain measures left or right. Therefore, this part of the graph is going to the right forever and represents positive infinity. So our domain for this graph is negative infinity to positive infinity. This is consistent with what we learned when we studied exponential functions for the very first time. Exponential functions of the form f of x equals b to the x power have a domain of all real numbers, negative infinity to infinity. Okay, let's talk about the range. The range is a measure of how high or low a graph goes, because range talks about y coordinates, and y coordinates measure up and down. So we can clearly see that this goes up forever, so our range is going to end with a positive infinity. And it tries very hard to go down forever, but it cannot get underneath this x-axis. And what is the height of the x-axis? That would be 0. So the range of the exponential function goes from 0 to infinity. And notice the parentheses in all four places. All right, we are now going to solve this problem, and we are going to transform our exponential function into a new function. So how are they different, and how does that affect the coordinates we have? Well, we have an x turning into a negative x, and we have nothing else at the outside turning into a plus 6 at the outside. Remember, your order of transformations says that vertical shifts have to be last. So we're going to do whatever this negative x thing is first. All right, so the observed change is a negative. That makes this a reflection. The location of the negative is inside the exponent, close to x. Now, you might be thinking to yourself, but wait a minute, there's no parentheses here. Well, that is true. There are no parentheses there, but a superscript with a smaller font size is in itself its own form of parentheses. We do everything that's in that exponent first before anything else. So there actually are implied parentheses here. So when the change is inside close to x, that makes it horizontal. When the change is a negative, that makes it a reflection. So this negative x right here represents a horizontal reflection. As with all horizontal transformations, it is the y coordinate that is affected. Excuse me, I apologize. It's the x coordinate that is affected. I'll say that again. As with all horizontal transformations, it is the x coordinate that is affected. And since it's a reflection, the x is all multiplied by -1. So x's times -1. All right, the other change that we see here is this plus 6. That plus 6 is outside far from x, which makes it a vertical something. Adding or subtracted is indicative of a shift. So this is a vertical shift. Vertical shifts behave the way you would expect. Positive or adding is up. Negative or subtracting is down. Well, this is adding, and so we're going to go up 6. Now, with a vertical shift, which coordinates change? It's the y coordinates. Whenever you have any kind of a vertical transformation, that affects the y coordinates. And if you're going up, that's adding, and so this is going to be the y's. We will add 6. All right, so we now have everything we need in order to get our new table of points. We're going to take the values in this table. The x's will all get multiplied by -1, and the y's we will add 6. Okay, so let's do the times -1 first. That's actually really easy. When you multiply by -1, it just changes the sign. So we're going to change the sign of all of these numbers, and we're going to get 3, 2, 1, 0, -1, -2, -3. All right, when it comes to these y's, we're just going to add 6. So for example, instead of e to the -3, now it will be e to the -3 plus 6. Instead of e to the -2, now it'll be e to the -2 plus 6. Actually, let me use these simplified fractions here. This is what Alex is going to want, the simplified fraction, the one that does not have the negative in the exponent. So instead of 1 over e cubed, we're going to have 1 over e cubed plus 6. Instead of 1 over e squared, we're going to have 1 over e squared plus 6. Instead of 1 over e, we'll have 1 over e plus 6. Instead of 1, we'll have 1 plus 6, which is 7. Instead of e, we'll have e plus 6, e squared plus 6, and e cubed plus 6. Now I'm going to give you a decimal approximation for every one of these. Well, except 7. 7 is just 7. And that's really easy to do because we're just going to take these decimal approximations and add 6. So we're going to get 6.050, 6.135, 6.368, 7, 8.718, 13.389, and 26.086. Okay, I'm just adding 6 to all of these decimal values to get the new decimal values. All right, so now that I've done that, I can go ahead and create my new graph. Let's plot the points. All right, so let's start with a nice easy one. Let's start in the middle of the table. 0, 7. That would be this point right here. All right, next, -1, comma 8.718. So 1 to the left, and then a little bit above 8. Actually, quite a bit above 8. 8.7 is more than halfway across. So that's going to be this spot right there. All right, -2 and 13.389. So -2 is here. 13.389 is almost off the chart here. All right, and there's no room for the 26. It's just that my graph doesn't go that high. 1 and 6.368. So that looks like that'd be approximately here. 2 at a height of 6.135. That looks like that'd be about here. And 3 at a height of 6.050. So we can see exactly what's happening with our y values. As we travel up the table, they're getting smaller and smaller and smaller, getting closer and closer and closer to, but never reaching the number 6. This allows us to put our asymptote on the graph. So let's connect our dots and then we'll draw our asymptote. So here's our exponential function. Okay. The original graph, the green graph, had the x-axis as its horizontal asymptote. But we noticed that the transformation means that we need to go up 6. Well, when you go up 6, that moves the asymptote as well. So instead of the asymptote being at a height of 0, it's now at 1, 2, 3, 4, 5, 6. It moves all the way up here. And our horizontal asymptote, this is the new line that the new curve approaches. All right, that just leaves domain and range for us to decide. So let's go ahead and do that quickly. Looking at the orange graph, let's start with this right here. This is very clearly pointing to the right forever, so our domain is going to end in positive infinity. This arrow is pointing in two directions, up and left. So think about those two directions, up and left. Which one do we care about for domain? That would be left, left forever. So my domain is negative infinity, comma, infinity. This particular transformed function did not end up affecting our domain. How about the range? Well, all right, this clearly goes up forever, so our range is going to end in positive infinity, but how far down does it go? Well, it goes down, 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 and then it would like to continue going further down, but it cannot get past this line at a height of 6. So that means that our range is from 6 to infinity, and again, parentheses in all 4 places. All right, there we go. We've now completed this problem, including finding the domain and range. We've got one more problem of this type left to go.